Hey there, welcome to my lab report for Lab 1 on constant velocity motion for Physics 2211. Today we'll be reviewing some of Newton's laws and how they correspond to this lab experiment that we're going to be doing. So first thing first, we're going to look at the purpose of the lab, which is going to be observing the concept of constant velocity as well as the principles of Newton's second law by comparing and contrasting the observed position of an object to the computation model of an object. So some assumptions we can make prior to the lab is that there's no air resistance or friction because they're going to be negligible in our computations. A brief preview of the lab is our object is going to be a golf ball, the observed position is going to be used by tracker, and our computation position is going to be calculated by glow script. Some fundamental principles we need to know first is Newton's first law, which is known as law of inertia, states that an object that rests remains at rest, or if in motion remains in motion at a constant velocity unless acted on by a net external force. Newton's second law, which is known as the momentum principle, states that the force is equal to the rate of change of momentum or mass times acceleration. So we see our net force is actually equal to our mass times acceleration here. Velocity is also known as equal to our change of position over change of time, which can be computed to be our position update formula, which is the final position equal initial position plus the average velocity times our delta t, or change in time. You can see down here, acceleration is equal to change of velocity over change of time, which can also be computed to be the velocity update formula. As you can see here, acceleration is also equal to net force over m. So procedures we need to know first is that we need to record an object rolling at a constant speed in a relatively straight line. Next, we need to import the video into tracker to go frame by frame and track the ball's position in each frame. Then we need to get data from tracker and import the initial position and velocity in the glow script to create a computational model. Then we need to import data from both tracker and glow script to compare and contrast the data slopes. And we're going to create a scatter plot that directly compares both data, so we can look at the slopes and compare and contrast both of those. Next, we look at this video here, which shows our golf ball and has it rolls along the desk and it hits this water ball. Our system is going to be the golf ball, which is moving along the desk. The surrounding is the desk, and our initial conditions is 0.000879 meters. Our velocity is going to be 0.2187 meters per second, which is calculated by velocity, which is equal to our change in position over change in time, also known as R2 minus R1 over T2 minus T1. We're going to be using these 2 points shown up here. At 0 seconds, we have 0.000879 meters. At 0.033 seconds, we have 0.007299 meters. And over this, our ball took 1.4 seconds from the beginning time to the end time where it hit the water bottle. So the code for computational model, our ball mass is going to be 0.046 kilograms approximately. Our ball position can be initially 0.000817 meters. Our velocity is going to be 0.817 meters per second. And something important to note is that this is only in the x direction because our ball is only moving in the x direction, not in the y direction or the z direction. That's why both these values are going to be 0. So our net force is 0 because our constant velocity means no acceleration and no net force, right? Which is derived from the F equals ma equation. One thing to note is our delta t is going to be 1 over 30 because tracker records at a frame of 30 fps. So it records at 0.033 seconds per data point. Our ball velocity, we can update it by using the velocity update formula, which is equal to our velocity of our ball plus net force over the mass of the ball times our change in time, or delta t. And then to update our ball's position, we just add it to the velocity of the ball, which is multiplied by our change in time. One thing to note is our velocity update formula is going to stay consistent because we know our net force is 0, thus it's going to look like ball.vel equal ball.vel, which is equal to each other. We can look at our computational model here, which is shown like graphically, visually. You can see we have a positive slope, and then our constant velocity, which is moving like that. We can look at our predicted versus observed graph. Our blues are predicted, the orange is the observed, with the same amount of data points for both lines. You see our predicted is a little bit skewed because it's a little inconsistent. There can be some errors when we talk about why there's so many inconsistent data points here. You see observed is a little more consistent because we use actual math and we computed it to be a bit more consistent. And this is not accounting for like the errors and stuff. We're neglecting air resistance, friction, and other surrounding factors. So to talk about the possible errors, we have human error, which is pushing the ball into a not straight line. I could have been pushing the ball into like a curve or at a really slight angle, and it's not going to be going in a straight line like how we predicted it to be, or how we wanted this lab experiment to be set up to be. The surrounding forces, we might have like an uneven surface where the desk might not be completely flat. We can have the force of friction, air resistance. These two are some factors we didn't really account for in computing our model. Position tracking, as you can see in this image here, my spacing between the 2 points, or the points in between the whole tracking, is really inconsistent, which thus is going to cause some inconsistencies in our computational model. So what if the x-axis were flipped, right? So if we switch the axis from positive x to negative x and positive y to negative y, the graph would be negative slope for negative x, and the negative y would have no change as our ball is only moving along the x-axis, not on the y-axis or the z-axis. The velocity as well would have not have any change to it because only the changes, signs, and velocity indicate the direction change, and it shows that we're moving in a constant velocity in the same direction. So you can see, like on that computational model video, we were moving a positive velocity, and that just indicates the direction of the velocity. So what does it mean? Is it possible to say how many pushes the polar add together give a zero net force? We can conclude that net force is indeed not zero, at least in the x direction, because this is shown in our predicted force observed graph, where we have two different slopes, which means that there are other unknown forces or factors at play that we do not account for. This could be air resistance or friction that we talked about earlier, and we just neglect these in our calculations. In the y direction, however, we know that the net force is zero because there's a force of gravity acting downwards in the golf ball, while the normal force is pushing up against the ball, which actively cancels out that downwards gravity or force of gravity. So that's all. Thank you for listening.